In this video, we're going to investigate a relationship between the ordinary generating function for a sequence and the exponential generating function for a sequence. But first, let's recall a couple of definitions and look at some examples. So the definitions first. So given a sequence, A0, A1, A2, A3, so on and so forth, the ordinary generating function for this sequence, which we'll call A of x, where x is a formal variable, is defined to be the sum as n goes from 0 to infinity of an x to the n. So in other words, the coefficient of x to the n in this power series is the nth term in our sequence. Then the exponential generating function for this sequence is defined as follows. We'll call it e of x. Again, x is a formal variable, and that'll be the sum as n goes from 0 to infinity of an over n factorial x to the n. So now if we extract the coefficient of x to the n from this power series, we don't quite gain the term from our original sequence. We gain the term from our original sequence divided by n factorial. And there's a time and place for each of these. If you've got some sort of sequence that has multiplicative recursion, probably an exponential generating function is the way to go. And I don't really mean multiplicative recursion like you are multiplying two previous terms, but maybe you're multiplying a previous term by a power of n or something. But if you've got maybe a linear recursion, you would use something like this. Another thing is that when you work with ordinary generating functions, you usually end up with algebraic equations that you need to solve for these ordinary generating functions. But when you work with exponential generating functions, you often have differential equations that you need to solve. Okay, so let's get to our first example, which is quite simple. Let's say we've got the sequence an, which is 2 to the n for n bigger than or equal to 0. So that means our sequence looks like 1, 2, 4, 8, 16, 32, so on and so forth. So this sequence definitely doesn't converge, but the convergence has nothing to do with being able to write down either flavor of these generating functions. Okay, so let's do the ordinary generating function first. So in this case, we'll have the sum as n goes from 0 up to infinity of 2 to the n times x to the n, because 2 to the n is the nth term here. But that's just begging us to kind of put this together into the sum as n goes from 0 to infinity of 2 times x to the n, for which we can use geometric series summation to sum this into 1 over 1 minus 2x. And that rational function is generally the way that we would write down the ordinary generating function for this sequence. Now let's look at the exponential generating function. So we've got e of x, in this case is the sum as n goes from 0 to infinity. Now we have 2 to the n over n factorial times x to the n. So I will again put the 2 to the n and the x to the n together like we have over here. That'll give us our sum as n goes from 0 to infinity of 2x to the n over n factorial. But that should be familiar as the Maclaurin series, or the series expansion of the exponential function. So that will in fact give us e to the 2x. That's what we would use as the closed form for this exponential generating function. So now that we've looked at a really basic example, let's find the exponential generating function for a famous example, and that is the Fibonacci numbers. So now we're going to find the exponential generating function for the Fibonacci numbers. We won't find the ordinary generating function directly. I've done that in a couple of previous videos, but we will use a result that's forthcoming to transform our exponential generating function into an ordinary generating function. Okay, so let's get to it. Recall that the Fibonacci numbers can be defined as follows. The 0th term is equal to 0, the first term is equal to 1, and then we've got this two-step linear recursion. F sub n plus 2 equals F sub n plus F sub n plus 1, and that holds for all n bigger than or equal to 0. Okay, so now we might set f of x equal to, like I said, we want to do the exponential generating function. So that'll look something like this. We have the sum as n goes from 0 to infinity, f sub n over n factorial x to the n. And now let's see how we can encode these two seeds into this function. Well, notice if we evaluate this function at 0, everything cancels except for the 0th term because that's a constant term. And we'll get f sub 0, which is 0. So here, f sub 0 is 0, or f of 0 is 0. Furthermore, we can isolate the x to the first term, which is f sub 1, by taking a derivative. So that gives us f prime of 0 is equal to 1. So let's see. This f sub 0 equals 0 is encoded via this equation, whereas this f sub 1 equals 1 is encoded via this equation. But the fact that we've got a derivative in here really gives us some motivation for maybe taking a derivative of this and forming a differential equation that this generating function satisfies. And in fact, since we have a two-step recursion, that motivates us to take a second derivative. So let's do that. We've got f double prime of x equals the sum. Now it'll be the sum as n goes from 2 to infinity. Why 2 to infinity? Because the first two terms will go to 0 with the second derivative, the linear term and the constant term. And then we'll have f sub n over, this is now n minus 2 factorial x to the n minus 2. That's because this exponent will come down and it'll cancel that n factorial down to n minus 2 factorial. Okay, so now let's re-index this a little bit. Maybe we could re-index this by replacing n with n plus 2. That's going to change our starting point from 2 to 0. So we've got the sum as n goes from 0 to infinity of f sub n plus 2 over n factorial times x to the n. But that's really good news because we've achieved something right here that looks like we can apply the recursion to. So let's do that. And we'll split it into two sums. So that'll give us the sum as n goes from 0 up to infinity of f sub n over n factorial times x to the n. So that's this term. And then plus the sum as n goes from 0 to infinity of f sub n plus 1 over n factorial x to the n, like that. And now we're going to do a change of index in this second one. And that's so that we can put it in terms of f sub n instead of f sub n plus 1. And let's maybe do that by letting n turn into n minus 1. So that's going to have the effect of changing that n plus 1 to an n. And then this will change to an n minus 1 factorial, and n minus 1 here. And then that sum will start at n equals 1. Okay, so now the change has been done. But let's notice that this guy right here is exactly our original function, f of x. And this guy right here is the derivative of our original function. But now let's notice that f double prime equals f plus f prime with the following two initial conditions. So that means our function f satisfies the following differential equation: y double prime minus y prime minus y equals 0, with y of 0 equals 0 and y prime of 0 equals 1. Okay, so let's take that data to the top and then we'll finish it off. So on the last board, we showed that the exponential generating function for the Fibonacci numbers satisfied the following linear, homogeneous, second order differential equation with constant coefficients: y double prime minus y equals 0, with initial conditions y of 0 equals 0 and y prime of 0 equals 1. So that means if we can solve this differential equation, we have a closed form for this, but there's a standard strategy for solving this differential equation. It has to do with looking at the so-called characteristic polynomial for this differential equation. The characteristic polynomial for this differential equation is given by u squared minus u minus 1 equals 0. So I'll let you guys look into the theory of solving second order differential equations on your own. I've got an old course where I did an entire course of differential equations, but I think it's due for an update. So maybe I'll do that over the summer. Okay, so anyway, we need to find the roots of this. The roots of this are most easily found using the quadratic formula. So that means we have u equals, so that'll be negative b, so 1 plus minus the square root of b squared minus 4ac, that'll give us 5 over 2. So that means we have 1 plus root 5 over 2 and 1 minus root 5 over 2. So 1 plus root 5 over 2 is the well-known golden ratio. We'll call that phi. And then 1 minus root 5 over 2 is, well, maybe it's like the radical conjugate of the golden ratio, but I'll call that psi. So we've got two symbols for this. Okay, so what does that tell us? That tells us that f of x is of the form, maybe I'll use constants c1 e to the phi x plus c2 e to the psi x. Again, we're using the standard rules for solving a second order differential equation. But now we can take the derivative of that pretty easily to get phi times c1 phi x plus psi c2 e to the psi x, like that. Then we'd like to evaluate both of these at x equals 0 to use the fact that we know initial conditions here and solve for C1 and C2. Okay, so this first equation turns into C1 plus C2 equals 0. And this second equation will turn into phi C1 plus psi C2 equals 0. But now it's pretty easy to see that C1 plus C2 equals 0 tells us that C2 equals minus C1. And I should have said that we have phi C1 plus psi C2 equals 1 because of that initial condition. I misspoke. Okay, but now we can plug this back here. And what will we see? We'll see that phi minus psi times C1 equals 1. That's what we get after factoring the C1 out. But that tells us that C1 is equal to 1 over phi minus psi. But given the flavor of phi and psi here, we see that their difference is exactly the square root of 5. So C1 is the square root of 5, and psi will be minus 1 over the square root of 5, like that. So that means we have a closed form here. The closed form looks like 1 over root 5 here and a minus 1 over root 5 here. Okay, so that's our nice closed form for our exponential generating function for Fibonacci numbers, where phi and psi are defined like that over there. Okay, so now that we've got this, I want to prove a general result that links together ordinary and exponential generating functions. Okay, so here is the promised proposition that links together the ordinary and the exponential generating functions, really without talking about the sequence in the first place. So what we have is a of x, in other words, the ordinary generating function, is equal to the integral from 0 to infinity of e to the minus t, e tx dt, where that e tx is the exponential generating function evaluated at tx, and t is being integrated out there. So in my mind, this really looks like some sort of integral transform that's like somewhat similar to the Laplace transform. So if anyone knows the name of this transform, maybe post it in the comments. Maybe post some applications. Can it be used to solve differential equations like the Laplace transform? I'm not actually sure, but I didn't try very hard to find out. Okay, so anyway, this proof is just a pretty quick calculation using an integral representation of the factorial. So let's maybe get to it. So we've got a of x is equal to, by definition, the sum as n goes from 0 to infinity of a n x to the n. Now we're going to multiply this inside by n factorial over n factorial. So in other words, we're going to multiply by a fancy version of 1. So that'll allow us to write an over n factorial times x to the n, and then times another n factorial. So notice the n factorial and the n factorial would most definitely cancel back to this right here. Next, we're going to use the gamma function expression of this So we've used this on the channel before. I'll let you guys look it up if you need a reminder. But essentially what it does is allows us to write n factorial in terms of an integral. And what integral? Well, let's write it down. Now we have the sum as n goes from 0 to infinity, an over n factorial, x to the n, and then that n factorial can be rewritten as the integral from 0 to infinity of t to the n, and then e to the minus t dt. So this is the gamma function, I think evaluated at n plus 1, just by the definition of the gamma function. You don't really need to know about the gamma function here. You can also solve this a number of different ways. You could maybe do induction to get from here to here. The way I like to do it without induction is to do a change of variables, where I think I set one of these equal to u or something, and it all simplifies out pretty nicely. Okay, so anyway, this is what we've got here. And now we can change the order of summation and integration and start putting it all together. So this is going to give us the integral from 0 to infinity. And now we'll have the sum as n goes from 0 up to infinity of, let's see if we can write this carefully, e to the minus t. Maybe we'll take this e to the minus t out because that doesn't depend on our summation. And then next we'll have an over n factorial and then x times t to the n dt. Okay. So, but this guy right here suspiciously looks like our exponential generating function, and in fact it is. It's just evaluated at x times t. So that gives us the integral from 0 to infinity of e to the minus t, e to the tx dt, which is exactly where we wanted to end. So now let's apply this result to find a ordinary generating function for the Fibonacci numbers. So this is overkill for doing that type of thing, but I think it's like a nice exercise nonetheless. So our two big results from this video are as follows. The exponential generating function for the Fibonacci numbers is given by this. And then this will relate the exponential generating function and the ordinary generating function. I've renamed my e as f here just so that it sets up for our example. But I've left this as a for our ordinary generating function. But maybe we'll change it. Maybe we'll change this to small f. So it's like small f is the ordinary and big F is the exponential. Okay, so now let's apply our result. So we have small f of x will be equal to the integral from 0 to infinity of e to the minus t. And then we have 1 over root 5. And then e to the phi tx minus e to the psi tx, and then dt. Okay, so that's what we get after evaluating this ftx, or this f of x at tx, and then plugging it all in there. Okay, so this is looking good. Now let's maybe take this 1 over root 5 out front. That's going to give us the integral from 0 to infinity of e to the, let's see if we can simplify this a little bit. So I believe we can factor a t out of this. And we will be left with phi x minus 1. Okay, so that's looking pretty good. And then we have minus. We can also factor a t out of this, and we will be left with psi x minus 1. Like that. But now this is dt. Now I want to be careful here because there's only a certain radius of convergence for these power series. So we can just assume that the x is within the radius of convergence and the necessary stuff goes to 0. So you guys know that I like to play it fast and loose with this kind of stuff. But if you want to check it out more carefully, I urge you to do so. Okay, so now we can take antiderivatives here. So essentially we've got a constant times t here and another constant times t here. It just happens that the constant is this thing that depends on x and phi. Okay, so let's see. This is going to give us 1 over root 5. And then taking the antiderivative here will be 1 over phi x minus 1. And then we have e to the t phi x minus 1 evaluated from 0 up to infinity, like that. And then something similar over here. So this will be minus 1 over psi x minus 1. And then we have e to the t times psi x minus 1 evaluated from 0 up to infinity. Okay, the important thing here is that we're only taking x values so that this number right here in these parentheses is less than 0. Same thing here, only x values, so this number in parentheses here is less than 0. But what does that mean? That means if we plug infinity, or really we're taking the limit as t approaches infinity, that will give us 0. Well, why is that? Because we've got e to a negative infinity, if you will, in both of them. That gives us 0. So that means all we're left with is the evaluation at 0. But notice the evaluation at 0 will turn both of them into 1. But it's the lower end point, so it comes with a minus sign. But I'll use that minus sign just to flip the order of subtraction here. And then we'll have 1 over the square root of 5, and then 1 plus 1 minus phi x, and then minus 1 over 1 minus psi x, like this. Okay, so that's starting to look good. And then actually from here, we could expand these as geometric series and get a closed formula for the Fibonacci numbers. But that's not our goal here. Our goal here is to take this and smash it together into one rational function that looks nice and is familiar to stuff that we've seen before. So let's bring that up and we'll do the last steps. So far we've determined that the ordinary generating function of Fibonacci numbers goes like this, and that was using the exponential generating function, which we calculated, as well as our proposition. So now we're going to use two facts in order to finish this off. First are the definitions of phi and psi, so half and then 1 plus or minus root 5 respectively. And notice they both satisfy the following quadratic polynomial. That's essentially how we got these numbers, is solving this quadratic equation. Okay, so now what I'd like to do is put these two guys together. So that means I'm going to take this term right here and multiply it by 1 minus psi x over 1 minus psi x. And then likewise, I'll take this one right here and multiply it by 1 minus phi x over 1 minus phi x. So let's see, that's going to give me 1 over root 5. And then I'll have 1 minus psi x. And then minus 1 minus phi x over, let's see what we get here. So that's going to be something like 1 minus phi x times 1 minus psi x. So that's what we get after like putting all the fractions together, if you will. Okay, so now let's simplify that out a little bit. Notice we've got 1 minus 1. That gives us 0 for the constant term here. We still have this 1 minus root 5 out front. And then we'll be left with phi minus psi times x in the numerator after all is said and done. And then multiplying this out, we will have 1. And then let's see what it is. It will be minus phi plus psi times x. So that's what we get for the linear terms. And then for the quadratic term, we'll have plus phi times psi of x. So we get something like that. And now let's get to simplifying. So let's notice that phi minus psi is equal to the square root of 2. Just look at the definition over there. But that's pretty nice because this square root of 5, I should say, cancels this square root of 5. So that's gone. And then we just have an x in the numerator here. Furthermore, phi plus psi is equal to 1 because the square roots of 5 cancel. So we get a 1 right here. And then furthermore, phi times psi is also equal to 1. And you can see that just from multiplying that out. Notice we get half times half, which is quarter. And then we have 1 minus 5, which will be equal to negative 4. So we have negative 4 over 4. I should say that this is negative 1. Okay, but then after all that simplification, we see that our sort of put together ordinary generating function looks like x over 1 minus x squared, which is kind of the standard format of the ordinary generating function for Fibonacci numbers. So I think that provides a nice gut check that the proposition that we proved, although we proved it is true all the time, works with a well-known sequence. And that's a good place to stop.